Now we come to the last section of this chapter and we will discuss the more realistic wave, that is the non-sinusoidal wave patterns. So far we have discussed the ideal wave, the sinusoidal wave, that is, we have the pure sinusoidal wave traveling in time. This kind of pure sinusoidal wave can be created approximately but close from the tuning fork, the one that can play the musical instrument may know this kind of instrument. That is, it is the shape of the frog, and when we hit the frog, it will create the sound wave that is almost give us the pure sinusoidal wave pattern. But in the real situation that we create the sound from the musical instrument, we get the oscillating pattern, but it is far different from the pure sinusoidal wave. For example, if you create the sound from the flute or from the clarinet and you measure the oscillation of the medium at a certain point, and you will have this pattern in time, okay, for the flute and for the clarinet, this pattern in time. We can see that we have the oscillating pattern, but it's not the sinusoidal wave. The question, you may have the question, so if in the real situation we don't have the sinusoidal wave, why we study the sinusoidal wave function? It is because even though in the real situation we have the wave that can be very different from the sinusoidal wave, we have a theorem with each, we call it the Fourier theorem. The Fourier, or if you use the French accent, you may have to read it as the Fourier theorem. The Fourier theorem states that you can create any kind of oscillating function or the periodic function from the sinusoidal function in terms of what we call the Fourier series. The Fourier series. The Fourier series can be written as the YT equal to the summation over n of AN sine 2 pi Fn T plus Bn cos of 2 pi Fn T. It means that the meaning of this series is that if you write down this series, and normally this is an infinite series, that you need the infinite terms in this series to create the appropriate wave. But the meaning is that for the appropriate parameter AN, BN, and Fn, which is the frequency here of the sinusoidal wave, AN, BN is the amplitude of these two sinusoidal waves, and with the set of appropriate value of AN, BN, and FN, you can create the function ft which have any waveform of your desire, okay, of your desire. But if we look again at this expression, this is in term of the series or the summation. So it means that we sum the sinusoidal wave, or we look at the interference of a lot of sinusoidal wave, and the resulting wave can become any wave that you want. So it means that if you want this kind of wave, you have to choose the appropriate value of the AN, of the BN, and the frequency FN. And that is the mathematical technique that we can use to determine the value of AN, BN, and FN. But that is beyond the level of our study here. So what I want to say here is just that we can create any waveform from the sinusoidal wave, and that's why the sinusoidal wave is important. And once we understand the sinusoidal wave, we can create any waveform from it. Okay. This, using the Fourier theorem, on the opposite direction, if we have the waveform like this, the waveform from the fruit, we can use the Fourier theorem to extract the value of AN, BN, and the FN. And that is the branch of the mathematics that is the signal analysis. That is, we want to know if we have the wave pattern, and we want to know the component of the sinusoidal wave in that wave pattern. And we can represent it by looking the spectrum of the harmonic of the wave pattern. For example, this is a spectrum of the tuning fork, which have only one frequency, so it is a pure sinusoidal function because it has only one component at this frequency. But if we look at the spectrum from the harmonic from the fruit and look at the spectrum, we have the first harmonic, the second harmonic, and the third, fourth, and so on. It means that other than the fundamental frequency, we have the higher harmonic in the sound of fruit. And this is the relative intensity that gives us the idea of how large or the amplitude of the frequency of the component at this harmonic. Okay, at this harmonic. And this is the spectrum of the clarinet. Okay, from this analysis, we can have the information of the component of the sound wave in terms of the fundamental sinusoidal wave, that that when we have the interference of all components, and it will give the wave pattern of our desire. Okay. Also, on the different direction, it means that we can synthesize any kind of sound wave by summing or make an interference of the sinusoidal wave from this expression. Now we have the instrument like that we call the synthesizer, and it can create any sound from any musical instrument and beyond, because it can make a bizarre sound and the sound that we don't have from any kind of musical instrument before. Okay. For example, we can create the sound wave that has the wave pattern as a square wave like this, and this can be done by many sinusoidal waves together to get this kind of sound wave. And from the modern synthesizer, you can create this simple square wave or any complex wave from the fundamental sinusoidal wave, and using the Fourier theorem that we have discussed.